And here is the agenda. So during the introduction, we will first give a brief review of the Resonant converter, and then discuss about the advantages of the LLC type converter. After that, following that, we will discuss some preconditions about the design. It includes the LLC converter configurations, operations, and modeling. After that, we will give a step-by-step design. We will summarize that. We will summarize all the step by step to get into a flow chart, and and also we will derive how the voltage gain functions. We will derive the voltage gain function. So this function is very important in the LLC topology. After that, we will go to the considerations when doing the design. So it also includes the voltage gain, the switch frequency, the line load regulation, and the zero voltage switching. Also, we will give an example of this to check if the steps are okay. Yeah. Now let's go into the introduction. At the on the left side, this is the service Resonant converter, and on the right side is the parallel Resonant converter. This two converter was discussed some time ago. Was first developed. So we will show the flaws and the advantage of this two converter. For the SRC, there are some issues with SRC. We can see that there's only single resonant frequency here. So the disadvantage is that when the SRC converter works at the light load, they need to increase the switching frequency a lot. But for the PRC, the resonance point changed with the load. So there's no such issue in the PRC converter. But as you can see that the load resistance is in parallel with this resonant network. So we can see there will be a large amount of circulate current here. So to overcome the shortage of SRC and the PRC, we need to combine then to LLCC, and we can see that this is the circuit diagram here on the left side. The LCC has two resonant frequency, and it will require three components here, right? So if we just change this resonant capacitor with an magnetizing inductor here, we will get an LLC. And for the LLC, the magnetizing inductor and the resonant inductor, we can integrate them into a transformer. So finally, we will get just the two components here. And also, there are some advantages of the LLC. It can achieve very high efficiency, and it also has less frequency variation and low circulation current. And it will provide ZVS over the entire operation range. This part is about the LLC topology. We can see from this, the LLC converter contains 3 main function blocks. One is the square waveform generator formed by these two MOSFETs, and the resonant network formed by the CR, ALR, and LM, and also the rectifiers formed by these 2 diodes, D1 and D2. So we can propose this equivalent circuit diagram, right? So from this diagram, we can see that if we change the frequency of this and the voltage across this R load, will varies. So this is how LLC worked. So, and we call the LLC is a frequency module converter instead of a PWM converter. And this part is about the operation of the LLC. We can see they have defined the three frequency here: the switch frequency, the series resonant frequency, and the circuit resonant frequency. And we can see that when the switching frequency is around the F0, actually a bit larger than this F0, the LLC will get the best performance. And if the switch frequency is above F0, we can see that the secondary side of the MOSFET, it will suffer some reverse recovery loss. But when if the frequency is lower than the F0, the secondary side is operating in DCM model, right? And that's to model the LLC converter, we can use this FHA. That means fixed harmonic approximation. This method can be used. And from this side, we can see that the input and output are both square waveform voltages. But in this network, the current is sinusoidal with a sinusoidal shape. So we can use the fundamental component to approximate the operation. And we can see that this switch node circuit can convert to this sinusoidal AC circuit. So we can use a AC circuit method to analyze the LLC. And here, based on this AC circuit, we can quickly get the voltage gain function. Yeah, we can easily see that this is a voltage divider, right? We can easily get this equation quickly. Yeah, it's very simple. And if we do some normalization, we will get this equation. This part, the F0, Q, Fn, and the FL is the parameters in this equation. Where we can define this and we list it here. And from this part, we draw this power plot, we draw this gain plot here based on the equation I mentioned in the previous slides. So for this plot, we fixed the LM. So we can see that when the QE increase, also we can also is the load current increase. When it increase, the peak gain will decrease, right? The peak gain will decrease. This is very important. We should remember this. And the second plot, the second gain plot, we fixed the QE. We fixed the QE and adjust the LN. When the LN decrease, the peak gain will go high, right? The peak gain will go high. And we should realize that if we want to achieve the rest, we want a small LN, right? But the small LN will lead to a large conduction loss. And now, so where to base a design on this gain plot. So I think the design can be made in the vicinity of this unitized gain. So at this, it can make a lightest frequency variation. And also we can see that the gain can be able to larger or smaller or just equal to 1. And also we should keep the LLC curvature work at the right side. Look at this, you can see this a dot, a slash dot here. We should work at the right side of the resonant peak. So the LLC will achieve the ZVS. And for the line and the load regulation, we should properly set up the maximum gain and the minimum gain. So we can see from this two equation, the gain is the maximum and the minimum gain is related to the V-in voltage and the V-out voltage, and also the turn ratio of the transformer here. Also, from this plot, we can see that when the load is 0, this load is 0, this curve, the cross of this limitation and this curve, we can get the maximum switching frequency. And from this curve to the max limitation, we can get the minimum switching frequency here. Before we go to the details, we should show attention to the two issues. And one is about the overload current operation. So when there is an overload current operation, what shall we do to avoid the failure of the primary MOSFETs? So we can do that. The basic principle of this is to make sure the LLC operates on the right side of the resonant peak. So we can choose this curve of the QE, the max. We can choose the QE at the overcurrent protection point. So at that time, this one will make sure this current will make sure the LLC will operate at the right side. But if there is a load short at the secondary side, what shall we do? because if there's a short at the secondary side, the cave of the gain, we can say that it will from the K1 to K2 to K3 to K4. And the K1 means the QE to equal to 0. This means there's a low load, and the K4 that means there's a very heavy load, means the shortage load. And we can say that inevitably, this will the LLC converter will work at the left side of this resonant peak. So what shall we do to avoid the primary MOSFET to failure? So there are three options here. First, we need to add some circuit to monitor the current here. And if there's a large current, we can increase the FSW, increase the switching frequency very quickly to increase the frequency very quickly to reduce the gain to 0. And the secondary side, options is that when we design the LLC, we can set the LLC work at this part with the FN is larger than the FN is larger than 1. So whenever there is a short condition in the secondary side, the minimal switching frequency is also larger than this. So there will be no issue here. And also the third option is we need to add independent protector functions. And this slide illustrates how to achieve the ZVS. From this one, this is the data time. At the data time, the Q1 is already turned off, and the Q2 is ready to turn on. So we can see that at the data time, the CDS, the voltage of the CDS will discharge. So the current will go through this. And when the voltage of the VDS, when the voltage of the Q2 goes to 0, and then the body diode of this MOSFET will turn on. So at that time, if we turn on the Q2, the Q2 will achieve the ZVS. So if we when we want to achieve the ZVS, there are two requirements here. So the necessary condition is we should the input impedance of the resonant network should be inductive. That means the voltage should be ahead of the current. And another thing is that the LLC converter should operate at the right side of the resonant peak. And about the sufficient condition is that we need to store enough energy in the mainly in the magnetizing inductor. So this current in the this magnetizing current will discharge the capacitors, mainly the CDS. Discharges the CDS. So another thing is we should receive enough time. That means the data time for the discharge time. For discharge, yeah. And in previous slides, we keep saying that we should make the LLC converter work at the right side of the resonant peak, but why? Why not on the left side? This is because if the LLC work at the left side, it will go to the capacitive current result. So that means the current will be ahead of the voltage. This will, for the primary MOSFET, it will lose the ZVS. And also, it will suffer a very have a reverse recovery loss, which will lead to the primary lead the failure of the primary MOSFET, and also it will lead to a higher EMI noise. Yeah. Before we go to the design, there are four parameters here we should pay attention to. The first one is the switching frequency, and this one is the transformer turn ratio, and also the inductance ratio, and the quality factor here. First, about the switching frequency. Usually, we just select the switching frequency below 150 kilohertz. So, and for the switching frequency, if we decrease it, the converter, the size of the converter will be very large. And also, if we increase the switching frequency, we should make a trade-off. We should compare if the ZVS benefit. We should make the ZVS benefit increase with the hard switch converter. Yeah, and if we want to make the LLC converter working, operating at a very high frequency, I think maybe we should concern about this. If there is a valuable component here for the high switching frequency, and also we should pay attention to the additional switch loss, and this parasitic effects. Yeah. This part is about the turns ratio, transformer turns ratio. Yeah, it is flexible. It is flexible because the gain of the LLC can be larger, can be around 1. So it is very flexible. But from the beginning, we can set the turn ratio to 1. That means the set the turn ratio to 1. That means when the input voltage and output voltage is the typical value. And for most of the time, the converter is working at the typical value. So if we just set the turn ratio to 1, we will get a best performance for the LLC converter. And this part is about how to select the LN and the Q. The LN and the Q, we should select the proper one to achieve the peak gain of the converter is larger than the maximum load, the gain for the maximum load. So we can start with this. For the LN to equal to 5 and the QE equal to 0.5. But we need to recalculate, recheck if this is a proper one. And yeah, this is a trade-off to select the LN and QE, because we need to consideration all these conditions here. So start with this one is okay, and we'll do some rechecks when we do the real designs. Here, I summarize the steps to how to get the parameters of the LLC converter, and we can see that this is the recheck one, the recheck process here. And now I will give a design example. Here is the specifications, and we can see that this one, we want to keep the switch frequency in the range of 16 kilohertz to 115 kilohertz. And this is the proposed converter circuit block diagram. And we can see this part, the TI part, UCC 25600 is proposed. And UCC 25600 is a high-performance LLC controller. It has two drivers here. And also, it provides the programmable data time, switch frequency, and the soft start time here. And it also includes some protection. And when the LLC converter is working at the light load, this controller can also get the converter operating at the best model. And here, using the flow chart mentioned before, we can get the detailed parameter for the design we mentioned for the design, and this is the turn ratio, LM, and LCR here. So we need to check if these parameters are good or not. Yeah, and this one is about the gain plot. The gain plot. We use the equation. We used the equation mentioned before to get this plot, and we can check. We can say that with the parameters we get, the converter can work well, very well. And this is maximum gain, and this is a minimum gain needed for the LLC converter. And we can see that at this point, the cap is below the minimum gain. So we can see that at the light load, there is no need for the converter to work at the best model, right? And also we can see that this LLC converter is working at the right side of the resonant peak. Yeah. For this one, we just do the calculations in serial. So in series. So I proposed us to do some circuit simulation here, because the method we used, the FHA, the method we used is just an approximate method. So there will be some difference between the real and this FHA method. So better to do some circuit simulation here. Then we will select the physical component here and build the PCB to do the benching test to verify if this is okay. If it's not okay, we need to adjust the parameters of this converter. And now this is the test result of the LLC. This is the efficiency, and this is the output ripple. And this tool is about the resonant network voltages and current. From this side, we can see that this current is negative. We can see that the MOSFET of Q2 can easily achieve the VS. And this slides compare the gain result, the gain from the test result and the gain from the FHA method. We can see that the red curve is based on the equation, which is the FHA method. And the triangle dot, this one is with test. So we can see that around the F0, the result is nearly the same, right? The accuracy is okay, but when away from the F0, we can see the difference between these two curves. So is that a big problem? Yeah, not. So this is just a little difference here. The FHA method can still can meet the engineering requirement in our design. At last, I will make a conclusion here, and we have proposed the FHA-based method to analyze the LLC converter, and then we proposed and then we summarized a flowchart to get how to design the LLC design step by step, and finally we give a design example about this to verify if this flowchart is okay or the staging is okay.